Okay, today we're going to be talking about new functions from old functions. So you guys pretty much know this as transformations. So basically, what we're talking about today has to strictly do with starting with our basic function and then transforming it to obtain our new functions. So what we're going to discuss in section 3 is that we will discuss properties of functions that causes a function to translate up or down, left or right, and we're also going to stretch and reflect. Okay, so what we're going to do here is I'm going to define kind of all at once when we see our vertical and horizontal shift, and then we'll also define where we see our vertical and horizontal stretches, and then we'll also graph, or I'll show you something visual that describes these. So let's define vertical and horizontal shifts. So if we have vertical, horizontal shifts. So let's start off with a statement, and you'll see where this statement comes in helpful. So suppose c is greater than 0, and the reason why we want c greater than 0 is you'll see because if we're trying to generalize our vertical or horizontal shifts, we want c to be a positive number so we don't contradict what we're saying. So to obtain the graph of the following, if we have y equals to f of x plus c, and see now what is it that we notice? This is going to create what type of a shift? It's going to create a vertical shift, and we're going to move it up c units. Now, how come I know we're going to move it up c units? That's why we have this condition where c is greater than 0. So it's just for the sake of being able to define this appropriately. So what y equals f of x plus c does, this shifts the graph of y equals to f of x up c units. And then, of course, if that's the case, we also have y equals f of x minus c, which then this would shift it, the graph of f of x down c units. So this shifts the graph of y equals to f of x down c units. Okay, and of course this makes sense to us. How come? Because we're grabbing the y values of these functions and we're adding or subtracting from the y values of the function, which is causing things to shift up or down. Okay, so now if I have y equals to f of x minus c, this notation actually shifts our graph c units to the right. So this shifts the graph of y equals to f of x right c units. Okay, and of course, if we have y equals to f of x plus c, this shifts the graph of y equals to f of x left c units. Okay, so the one thing that people usually find weird about these conditions is it's kind of like we're forced to think in the opposite way. So since this is x minus a number, this is shifting it to the right. Or this is x plus a number, this is shifting it to the left. And sometimes people ask, well, why does that work that way? And the simplest example I could give you just to kind of point this out is take into consideration, let's pick a very simple function, f of x equals to x squared. Okay, so here's what we're claiming. Um, this graph is a parabola. And if I grab and ask you to kind of compare to f of x equals x squared of f of x minus 2, which essentially is the same thing as x minus 2 quantity squared, you would say that this graph is the same thing as its parent graph, which is x squared, except it's been shifted 2 units to the right. And the question is, well, how's that the case, or why is that true? Well, think of it this way. Whatever y values that this guy hits, this function will hit the same exact y values, except at different x values. So think of it this way. Let's pick a random x value for x squared, and let's pick 3, for instance. So if I plug in 3 into this function, my output is going to be a 9. So now my question is, well, what must I plug in for x here to get the same output as this function? And the answer is, well, whatever this is, whatever I plug in for x here, I need to make sure whatever I plug in and I square this, I end up getting a 9. So if you think about this, I need to plug in a 5 for x. So if I plug in a 5 for x, what do I notice? If I replace 5 in for x, which gives me that, which essentially is going to be the same thing as 5, or it's going to be the same thing as 5 minus 2 quantity squared, which ends up being 3 squared, which is 9. And so notice how, of course, over here I plugged in 3 for x and I plugged in 5 for x. So what does this mean? This has gone to the right 2 units. Okay? So that basically takes care of why these are kind of treated in the opposite manner. Okay? So moving on to the stretches and compressions. So now our focus is going to be on vertical and horizontal stretching, and of course we'll talk about reflections as well. Okay, so let's set another condition. So we're going to say suppose that c is greater than 1. To obtain the graph of, and let's start off with y equals to c times f of x, which essentially we're just grabbing this function or the y values of the function and we're multiplying it by some number that's greater than 1. And anytime you multiply a number greater than 1 to another number, that number becomes larger. So what we're really doing here is we're making the y values larger, which essentially means we are stretching this vertically. Okay, so this would stretch the graph of y equals to f of x vertically by a factor of c, not x, by a factor of c. Okay, so if we have y equals to 1 over c times f of x. Now what I'm doing is I'm making my y values smaller. So now we're compressing vertically. So this compresses the graph of y equals to f of x vertically by a factor of c. Okay, so we are compressing, we're basically dividing out the y values by that number c. Okay, so we're making them smaller. And then we have, well, and notice how these are compressing and stretching vertically because I'm changing my y values. So, and when we're talking about vertical, when we're vertically compressing or stretching, we are affecting our y values. To horizontally stretch or compress, we need to deal with the x values. And so notice how this next statement is going to kind of multiply by some number to the x values before we find the y values, and that's what causes the horizontal compress or stretch. So this actually compresses the graph of y equals to f of x horizontally by a factor of c. Okay, and of course, if I have y equals f of 1 over c times x, or x over c, whichever way you want to put it, this stretches the graph of y equals to f of x horizontally, or not horizontally. Yes, it does. It is horizontally. We just spent some time talking about why it's horizontally. Horizontally by a factor of c. Okay, and so there we have it. So these are basically all of our stretches and compressions. So just really quickly, just to assign some visuals to this, let's graph these out. So, and I'm just going to use just a basic graph. So let's start off with this guy. And let's call this y equals to f of x. So if I shift this to the right, it's going to look like this. And the new notation that would describe this graph would just be y equals to f of x minus c, which means I'm shifting its c units to the right. If I grab this graph and move it to the left, it would just be y equals to f of x plus c. So I'm just grabbing this graph and moving it c units to the left. If I shift this up, it would be y equals to f of x plus c. And if I shift this down c units, it would be y equals to f of x minus c. Okay, so as far as the compressions go, the visualization of the compressions and stretches horizontally will have something like this. So once again, if I start off with y equals to f of x, and if I compress it vertically by a factor of c, which would do something like this, that would mean I am multiplying f of x by 1 over c. And if I want to stretch it vertically, then I would multiply it, which, by the way, notice how I'm kind of drawing this as if it's increasing faster because I am, after all, multiplying it, which is causing it to stretch. So it'd be c times f of x. Okay, and then, of course, we could have our reflections, which I haven't talked about, but we all know to reflect f of x about the y-axis, I just grab x and I replace it by a negative x. So that would basically give me something like this. and this is found by f of negative x. And if I want to reflect it about the x-axis, I'm multiplying the y value by negative. So if I do this, for example, that would be y equals to negative f of x. Now, I also know that your analysis teachers probably have told you this in the past. When you're asked to graph a function using transformations, if any type of reflections exist, always, always, always reflect first. Okay, because if you don't reflect first and you reflect at the end, you're more likely to make a mistake and get the incorrect graph out of this. So if you have more questions on that, I could kind of show you an example of it in class, and feel free to ask, and I'll be more than happy to show you what I mean by that. Okay, so let's look at our first example. So we're going to say sketch the graph of y equals to cosine of 2x. Okay, so if we look at this and we compare this to its parent graph, its original graph is just a basic y equals to cosine of x graph. Okay, and so here's what we know. And I'm only going to graph one period of this because we all know that these are periodic functions. And we know that the cosine of x has a graph of what, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And this is 1, negative 1, and 1 period of cosine looks like this. Okay, now, how do I convert cosine of x to cosine of 2x? Well, if we look at our notes earlier, we said since c is greater than 1, which it is, and in fact, what am I doing? I'm making x larger. So what I'm really doing is we are compressing this horizontally by a factor of 2. So in other words, what does that mean? I'm grabbing all my x values of my original functions, and I'm cutting them in half. And that's where I'll get my compression. So y equals to cosine of 2x will now look like this. My x values, so notice how when you're compressing horizontally, we're only affecting our x values. Our y values don't change. They stay the same. So basically, for example, for y equals 1, the x value is 0. So if I cut 0 in half, it's still 0. So when x is 0, my y value is still 1. Okay, however, when my y value is 0, x is pi over 2. So this guy is now going to hit y equals 0 when x is pi over 4. So that's where it's going to be. And then it'll hit y equals negative 1 when x is pi over 2. And it'll hit y equals 0 again when x is 3 pi over 4. And finally, it'll complete its cycle, or its period, when x is pi. So basically, it's going to look something like that. So I know that, you know, if you compare these side by side, it looks like it's almost the same graph, but if you notice, its x values have been cut in half. So this is basically, it's like we grabbed it and just compressed it, and that's basically what we did here. So there you have it. We just sketched the graph of cosine of 2x by using a horizontal compression. Okay, so moving on. Now what we're going to do is we're going to talk about combining functions. So the main key here is we're just going to grab two different functions and we're going to put them together. So we care about the combination of functions. Okay, so that's our focus is going to be, we're going to grab two functions and we're going to combine them. So we are going to say, let's kind of define this. So let f and g be functions with domains A and B. Okay, so then the functions f plus g, f minus g, f times g, and f divided by g are defined as the following: f plus g of x, which literally is saying the same thing as, so this notation might look weird, but this is literally saying the same thing as f of x plus g of x. Okay, and so then this would also have a domain of equal to of A intersect B. So in other words, here's what we're saying. We're taking, if you've never seen this notation, this just means it's an and, or it's an intersection. It's what A and B have in common. So for example, if f is defined everywhere, but g is defined only in the positive numbers, then f plus g will only be defined where their domains are in common. So then their domain would just be all positive numbers, because although f could be anything, g is not defined everywhere. So that's where we kind of have to stick with the restrictions. Okay, and we'll do an example in a minute, and you'll see how that works if you're kind of stuck or not clear with what I'm saying here. Okay, so let's move on. So f minus g of x means the same thing as f of x minus g of x. And once again, their domain just equals to what A and B have in common, or what f and g have in common, just the x values that exist in both. Okay, now we have f g of x. This is the same thing as saying f of x times g of x, which once again the domain is what f and g have in common again. Okay, so if you remember, if we look back at our notes, we defined the domain of f to be A and the domain of g to be B. So if you're wondering where I'm getting these A's and B's from, it's just what we define them as. Okay, so of course every function is going to have a different type of domain. Okay, and then of course f divided by g of x is going to be the same thing with one restriction, and I'm sure you can guess. Their domain should be everything that they have in common. In addition, we want to make sure that g of x never equals to 0, because obviously we cannot divide by 0. So the domain here is going to be the set such that x is in A and B, such that g of x does not equal to 0. Okay, now here's another notation that I'm going to introduce you to. This weird looking E, which it's not really an E, but I guess it looks like one. So this is the mathematical notation saying that x is inside of A and B. Okay, so this basically means in. So if I tell you, for example, x is in, let me make up an interval, the interval 1 comma 2, that means x is a number in this interval from 1 to 2. Okay, so that's all that means. Okay, so keep that in mind. This just means this is an element inside of that. Okay, so let's look at our second example. So we're going to say find f plus g and f divided by g, and state their domain given that f of x equals to x cubed plus 2x squared, and g of x equals to 3x squared minus 1. Okay, so let's look at this right away. Before we actually find their sum, let's find the domain of each separately. So the domain of f is all real numbers. Right? It's a polynomial function, and polynomial functions are defined everywhere. Same thing with 3x squared minus 1. The domain of 3x squared minus 1 is all real numbers as well, because, once again, it's a polynomial function, so they're defined everywhere. So to find f plus g of x, that's just adding these two together. So then x cubed plus 2x squared plus 3x squared minus 1 becomes x cubed plus 5x squared minus 1. And of course, the domain of this new function is basically what f and g have in common, which basically is all real numbers. So the domain here is all real numbers. Okay, now f divided by g of x would just be x cubed plus 2x squared divided by 3x squared minus 1. Now, the one thing we need to be careful about here is that the domain of this, although they both are all real numbers, that's they have in common, but I just need to make sure that I exclude any x value that would make my denominator equal to 0. So obviously we all know how to do this. We would just set this equal to 0 and we'd solve for x. So what does that give us? 3x squared equals to 1, and then x squared equals to 1/3, which then x is plus or minus 1 over rad 3. And in calculus, we don't need to rationalize. You could leave it as is. I mean, whether you write this as rad 3 over 3 or 1 over rad 3, numerically speaking, it's the same thing. Okay, so we're interested in doing more important things or more interesting things than just to waste our time to rationalize. So you could leave it as plus or minus 1 over rad 3. So in fact, what don't I want? The domain of this is all real numbers except for plus or minus 1 over rad 3. So in interval notation, that would be negative infinity to negative 1 over rad 3, union that with negative 1 over rad 3 to 1 over rad 3, and union that with 1 over rad 3 to infinity. And I'm pretty sure you guys are comfortable with interval notation because I feel like that's practically all that we did in analysis. All right, so let's move on to the last topic of this section, which has to do with composite functions. So composite functions. And this is another way of kind of like combining two functions together. And it's like we're plugging in one function into the other. So this is another way of combining functions is through composite functions. Okay, so you know, to put it differently, or to kind of go into a little bit of detail as to what a composite function is, we could kind of say a composite function is a function created by plugging, and let's put these in quotation marks. I mean, we're plugging in kind of one function into another function. Okay, so before we do a couple of examples, let me just define one more thing, and then we'll make a comment on composite functions, and then we'll finish this section up with a couple of examples. So let's talk about this definition. So given two functions f and g, the composite function f of g is defined by the following: f of g of x, which you're probably more used to seeing this rewritten as the same thing as f of g of x, okay, which basically this is saying what? Plug in the function g into the variables of f. Okay, that's basically what this is. So this is saying plug in the function g into the variables of f. That's basically what it's saying. One last comment I want to make. Note, and maybe you should think about this. Does f of g of x equal to g of f? And the answer is no. Okay, so f of g of x does not equal to g of f of x. And in fact, anytime we make a comment, so this is not always. And, if you remember back in analysis, the only time f of g of x will equal to g of f of x is that if f and g are inverses of one another. Other than that, the order is very, very important. So you could find f of g of x, and you could find g of f of x, and they will not be the same function, okay? Like I said, unless they're inverses. And in that case, both of them will equal to x, okay? So just keep that in mind. The order of composite functions is very important. Okay, so let's finish this up with the last two examples. So for example 3, find f of g of h if f of x equals to x plus 1, g of x equals to 2x, and h of x equals to x minus 1. Now, this is a composite function of 3 functions, which is fine. Just because we defined it for 2 functions up here, it doesn't mean that when we talk about composite functions, it has to be 2 functions. So by definition, if we want to find f of g of h of x, that's by definition the same thing as f of g of h of x. So we have to go in steps here. So we work from inside out. So this is saying, look, go to your function g, and in place of the variables, plug in h. So let's not worry about the f just yet. So what is this going to look like? So this will be f of, so in here, what I'm going to do is I'm going to go to the function g, which is 2x, and in place of x, I'm going to replace x with x minus 1, because that's what h is. So this is going to turn into what? 2 times, and instead of x, now I'm going to replace x with x minus 1. Which then, if we want, we can slightly simplify this, which becomes f of 2x minus 2. Okay? And then what is this saying? Go to your function f, and anywhere you see a variable, replace it with 2x minus 2, which that becomes, x is what? X plus 1. So it'll be what? 2x minus 2 plus 1. Remember, this plus 1 is coming from that plus 1. And simplify this, and you get a new function, which is defined as 2x minus 1. Okay? So there you have it. Now, the last example I want to do, we are kind of going to go backwards. Okay? So what we want to do here is we're going to be given a composite function, and we're going to say come up with 2 functions where when you find their composition, you get this function out of it. So for example, express the function in the form of f of g. So here's capital F, which is x squared plus 1. So to the power of 10. So think of it this way. What this question is asking is, can you come up with two functions, f and g, where when you take their composition, you get capital F? So in other words, we want to find f and g such that, so st means such that, okay, so that's such that f of g of x is the same thing as capital F. Okay, so the key here is I need to find two functions where when I take their composition, I get capital F. So think of it this way. It's kind of like I need to plug a function into capital F. So if I come back up here, I could already see it, can't I? In some sense, because I could see that, wait a minute, look. It looks like I've grabbed some function that was to the power of 10 and I replaced it with x squared plus 1. So just by looking at this, it kind of gives it away to us. So what we're doing is we're saying, look, why don't I let g of x equal to x squared plus 1? And what does that mean? I just took care of the x squared plus 1. So what's the only thing that's left? The function that's to the power of 10. So what does that mean? We could say f of x would be x to the power of 10. So notice how I came up with two functions, f and g. Now let's verify this. F of g of x is the same thing as saying what? F of x squared plus 1. And this is saying do what? Go to your function f, and anywhere you see a variable, replace it with x squared plus 1. And f is what? Just x to the power of 10. So I'm going to replace x with x squared plus 1, which gives me x squared plus 1 to the power of 10, which then that is actually capital F of x. And so there you have it. So my solution are those two functions. Now, you might be wondering, are these the only two functions I could come up with where when I take their composite function, I get this? And the answer is probably not. You could probably come up with more functions, except this is probably the simplest way out of this. So for homework, whenever you work on these, you just need to keep an eye out for the main function and see if you could find two functions within that one main function. And that pretty much gives it away from you, gives it away to you. Okay, so that basically takes care of section 3. We will continue on with section 4 the next time around. Okay, take care.